We have sort of a series of 3 lectures, sort of have these in chunks, right? And this is where we're going to first start talking about and getting into so-called pulse sequences. And I'll explain what a pulse sequence is. Some of you maybe know it already. And so this is the first lecture that we'll talk about sort of how we keep track of the magnetization after a series of events, in particular RF pulses today. And then as things develop, we'll be adding RF pulses and gradients and talking about imaging. So the next 3 lectures are really about saturation and inversion recovery today, and then we'll introduce spin echoes, and then we'll introduce gradient echoes. And that'll be kind of, then you'll have your sort of toolbox for understanding MR signal generation, and then we really get into the imaging parts of the course. So then just kind of a quick reminder of where we were last time, right? So we were introducing sort of this hardware component, the gradients. And there's probably a few sort of key things to remember about the gradients. You will recognize sort of physically sort of where they reside and where they lie. And we talked a little bit about how we run currents through these things and generate a linear variation in the magnetic field, but specifically it's a magnetic field that points along the z direction. So we always talk about B as being B fields, subscripted as G when we're talking about the gradients. It's a little clunky, but it's pretty specific. We indicating here as well that it points along the z direction. And in this particular case, the B field is a function of the x spatial position. Why is it a function of the x spatial position? Because for this specific example, we're talking about an x gradient, and that depends on x position. And so you could do the interesting thought experiment. Let's say we turn on a g gradient, but we consider spins. We consider a spin at isocenter to begin with, the simplest case, right? So what's the B field from the gradients for a spin at isocenter? 0. Right? So there's no x coordinate, so you're at isocenter at 0. That's the trivial case. What happens if I turn on an x gradient but I move along the y direction? What's the effect on my B field? An x gradient but I move along y. What's that? It's nothing. Right? And so the dot product, right, if you think of these as vectors, the g vector would be like a 0, sorry, this is an x gradient, so it would be something 0, 0, dotted with a position that would look like, we said it moved along y, so it wouldn't really matter, right? Does that make sense? Let's see if I can do it here. And so this here was g dotted with r, right? That was the most general form. Oh, was it slow? Sorry. The network's a little funky today. And so the G that we were just describing, right, would be would have a GX component, but it would have no Y, and it would have no Z component. Sorry, that's really laggy. Hopefully, we'll see if we have to do a reboot. And then the R vector that we were just considering, right, was excuse me, equal sign there, was something that we don't. We say we didn't have any x position, but we had some y position, but we didn't have a z position. And so the dot product of those 2 vectors, of course, is still going to be a 0 vector. And so it's kind of interesting, right? You can turn on an x gradient, you move along y, nothing happens. Turn on a z gradient and move along x, and nothing happens. And what ends up being important in MR is the fact that we can come up with linear combinations of gx, gy, gz to manipulate spins along sort of any direction within the scale. Yeah? And so then we stepped back and said, okay, we sort of understand physically what the gradients are all about. Mathematically, how do we deal with them? And the condition that we thought about again was free precession. We cared about free precession in the rotating frame, right? From here on out, we're really sticking with the rotating frame, and I probably won't even always point it out anymore. So if we think about free precession in the rotating frame, but we apply gradients, we do the normal. We start with our definition for B effective, but we have to figure out how to squeeze in a definition for the gradients in the rotating frame. And so that just comes out, we have the presence of the B0 field as well, and so our B field in the rotational frame is just B0 plus G dot R, and then this simplified out just to show only the effects of the gradient, basically, for the B effective. And then that goes back into our equation of motion in the rotating frame. And so then we recognize that this is going to give us a system of equations. We can partly expand those expressions to begin seeing what that system of equations would look like. And then I didn't actually show you this final result here, right? So this final result tells us, or in fact it looks a lot like free precession in the lab frame as a consequence of B0. But here, these are really the expressions of free precession in the rotating frame as a consequence of the gradients. Mathematically, they look really, really similar. And what it tells us is that the x and y components of the magnetization will be affected or impacted by the gradients. And that's really interesting, right? So the gradients can't affect the Z magnetization, right? They can't directly act on the Z magnetization. They can create magnetic field gradients in x, y, or z, and that can give us this spatial distribution of frequency or phase. But as a consequence of this expression here, the solution of which is these expressions here, the gradients can't act on the Z component of the magnetization. So conceptually, that's a good thing to kind of absorb. And then all that we see on the mx prime and my prime terms is that this looks like a rotation. It's a cosine term and a sine term, and it tells us that our spin can be acted on by the magnetization to rotate. And in fact, how much it rotates or even what direction it rotates in the rotating frame depends on the applied gradient strength and the position. And the applied gradient strengths can be positive or negative, right? We can have positive gradients, we can have negative gradients, and we can have those on any axis. And so there's lots of, there's a variety of ways in which we can sort of manipulate the spin system. But this will always be the case. The gradients only act on transverse magnetization. They don't have an effect on the Z component of the magnetization. That assumes all the things that we talked about in the last lecture, which is that we don't have Maxwell fields, we don't have these other sort of imperfections in the field. So again, I didn't show this explicitly last time. What we showed was that we would get, I think it's on the next slide here, it shows up here. So this is what I showed you last time, was that the frequency term that's inside here, there should probably be a T in there, right? Gamma times B, yeah, there should be a time in there, right? So we have gamma, okay, so we have gradient times position, that gives us field, right? We have field times gamma, and that gives us like megahertz or something like that. So we still need a time in there, sorry, that didn't make it this morning. And again, there should be a time on this as well, which is just to say this is what the frequency is well, actually that doesn't have time, right? This is the frequency as a consequence of the applied gradient and the spin position itself. And so what this told us was that the frequency of free precession, how much the spins are moving around in the rotating frame, is a function of space, right? It depends where you are relative to isocenter when you have an applied external gradient. Did you catch the typo here? It goes back to the previous slide. And then this is, that's correct. Okay, so that's the effects of how frequency can be manipulated, how we can manipulate the frequency of the spin system. And the other thing we talked about is how we can manipulate the phase of the spin system. The phase just tells us at a particular point in time where is the spin lies, is it oriented along X or Y or someplace else. And phase is related to frequency just by integrating. How long do you persist at that frequency? How long are you precessing around at a particular frequency will tell you how much phase you've built up. And so we just can integrate the frequency to tell us about the phase. And so we had a simple expression on the bottom here, which just said the amount of phase that your spin will accumulate depends on, always on gamma, depends on the magnitude of the gradient field, depends how far away you are from isocenter, and it depends how long the gradient is turned on for. Right? And we'll do this a lot. You'll see this when we start talking about phase encoding. This is the principle of inducing phase in the spin system. The idea of phase encoding is that we'll turn gradients on for brief periods of time, and we can store phase in the transverse magnetization. Is there a question?
Yeah. So with the terms in the top, would that be T grad? That would go with them.
Yeah. So these would just, I would have these just as general expressions. They depend on time, right? So however long that's going. The specific example that I'm thinking of. Sorry. Yeah. And so the example I have in mind here is just a gradient that we turn on for some finite period of time, right? So this is 0, showing it. Yeah. And then this would be T grad. this would be just the general expression of what happens, and so each of these are quite sure at time. So, and this you could write as like a function. Okay? So, tricky details, right? Okay. So, again, the principles there were beginning to give you some insight as to how gradients can be used to manipulate frequency or phase of the spin system, and that'll play an important role when we get to imaging. And so this is what we're going to be doing today. We're going to be talking about what is image contrast. We're going to talk about T1 weighted versus T2 weighted images. We'll start beginning to talk about pulse sequences, and we'll really spend most of the time on two particular pulse sequences. Where we use saturation pulses. From your homework, you probably hopefully remember what a saturation pulse is. What's the flip angle for a saturation pulse? 90, right? You're just saturating the transverse plane. And then we also have inversion pulses, which you all know are 180s. And then we'll talk about some kind of specific pulse sequences that make use of saturation pulses and inversion pulses as well. So that's kind of where we're headed. Image contrast. Why do we care so much about image contrast? There's probably a couple of reasons for this. I always like pointing out that as visual observers, what your brain is really good at is detecting contrast. You can see signal differences between things. What you're much less well good at is detecting what we call luminance, like how absolutely bright or dark something is. You can see that there's differences. Your eye is much more sensitive than, say, most digital cameras, for example, even film cameras. But when it comes to saying, oh, that's this bright, that's that many photons per unit area coming into my eyeball, you're actually pretty bad at that. And so the way I try to convince you guys of that is by saying, well, which is brighter, right? Brightness is a measure of luminance, right? How much signal is coming out of something. So raise your hand if you think A is brighter than B. It's a trick, some of you have seen this already, right? No one wants to answer. So then raise your hand if you think B is brighter than A. Right? So it's a little weird, right? Because you look at it and say, well, come on, B it can't possibly be like brighter than A, right? There's a checkerboard pattern there, for God's sake. But if I light up a little area there, and then I think I slide it over, just to convince you there was no actual trick there. The luminance of A and B were the same, and of course it's an optical illusion because of the shadow that comes from this funny little green tower. So again, the point is, you have no problem identifying a checkerboard pattern there, right? But if I didn't sort of trick you, you would have a hard time judging sort of how bright things are. And MR is not really good at, it's not a PET detector, it's not a photon counting CT machine, it's not SPECT, right? It ultimately goes through a really complicated receiver chain, and it turns out it's inordinately complicated and nobody can really figure it out. There's only one guy I know that's tried that could turn MR into a machine that's quantitative in the sense that the voltage you receive tells you something really directly about the number of spins or something like that. So that's, in my view, sort of a real open challenge for MR right now. But we've said it before, MR is really great at contrast, right? One of its main strengths is so-called soft tissue contrast, and so that's what I'll try to convince you today that we can do with MR pretty well. Something to keep in mind in all this, like why do we care about contrast so much? Why do clinicians in particular care about contrast so much? So here's two comparisons. A bunch of objects on the left. This is through simulation. So you've got high contrast objects on the top and lower contrast objects on the bottom, and then obviously large to small objects. And in the presence of noise, it becomes variously, in various ways difficult to detect some of these objects. It's perhaps obvious that small objects are harder to detect. But if you're small and pretty bright, you and I can still pick it out as a visual observer, right? Computers even have a hard time with this. If you're low contrast but you're really big, you can maybe just barely make out the bottom left there as there possibly being an object there. So obviously large and high contrast objects are easier to see in the presence of noise, and our systems are always noisy, so we're trying to maximize the contrast in general and try to minimize the noise. Too much technology. So hopefully is that resolution? Yeah, okay, right. And so sort of stepping back to that same idea, here you've got a range of sort of high contrast to low contrast objects, and looking at the difference of, in the presence of noise, here the noise is actually controlled. Is it easier to detect something when you have low resolution on the right-hand side or when you have high resolution? And obviously higher resolution images, it's easier to see these small kind of low contrast objects, and they're completely washed out in the low resolution image. So amongst the challenges in MR, of course, is that clinicians always want high resolution, right? What's the penalty in MR of acquiring high res?
So you have more noise.
Yeah, so noise is a big competing factor. As our voxel size gets smaller and smaller and smaller, we have less signal, right? There's less spins in that voxel, but the noise of the system hasn't changed. So the signal's dropping and the noise is constant. The signal to noise is crashing off. What's the other downside to high resolution? It's going to take time, right? So it kind of stands to reason. We haven't gotten to the procedure of how we acquire images in the first place, but higher resolution requires much more time for imaging. So there's a lot of competing interests here, right? Clinicians want high signal to noise, high resolution, fast, right? And that's not, those don't play well together. Okay, so what do we mean by contrast? This came up a little bit in your homework assignment. Here's a slightly more rigorous definition, which just says the contrast between two things you care about, object A and object B. It's just the magnitude of the signal intensity difference. So the pixel signal is the signal intensity, or you can get the signal intensity. And then we divide it rather by some reference. And that's a measure of contrast. We're not talking about contrast to noise yet. Noise is another consideration that will come up in the class later, but just a definition for contrast. And amongst the challenges in MR is how can we generate, okay, so the first thing is the contrast in MR, that is to say the signal difference between tissue A and tissue B is a function of a bunch of different things, right? We know that the tissue properties of A and the tissue properties of tissue B are going to have different proton densities, different T1s, different T2s, different T2 stars, maybe different diffusion, maybe different perfusion, different susceptibilities, like the list really goes on and on. And one of the goals in MR then is how can we manipulate the way we're doing the imaging experiment such that the contrast becomes approximately a function of just one of these things. Right? So we'd like to generate images that are just dependent on T1 and sort of orthogonalize or separate out these different tissue properties, right? There are reasons, there are examples of when we sort of mix these things on purpose, but the principle that we'll be talking about today is how can we manipulate the contrast of an image to be largely dependent on T1 or largely dependent on T2. And that means we have to understand enough about the physics to push down the contributions from, say, T1, when we want a T2 weighted image, or push down the contributions from T2 when we want a T1 weighted image. And so when we describe the contrast as being a function of T1, we refer to that as a T1 weighted image. And similarly, if we have it as a function of just T2, then that's a T2 weighted image. And so to get into how we can go about manipulating the contrast, we have to begin talking about pulse sequences. You have some expectation for this already because we've shown you RF pulses and inversion pulses and how the signal recovery curves for these tissues are different. But we need to sort of get comfortable working with the actual mathematics of it. And so what is a pulse sequence? Well, this is one pulse sequence, right? This is sheet music, which is just a timing diagram of playing music, right? It's a set of instructions that tells you from left to right what you're supposed to be doing. And a pulse sequence is really just the same thing. It's a set of instructions that tells the scanner from left to right. These are axes of time. And it's telling us what's happening to the RF pulses, or the V1 field, what's happening to the X gradient, the Y gradient, and the Z gradient. And as you become a sort of a 9-dan player of pulse sequences, you can sort of read these things and understand what's happening to your signal in the first place. And so this is what we'll be talking about today, is how do we keep track by hand, analytically, of what's happening to magnetization when we have a given or particular pulse sequence. Now it turns out it actually can get very complicated, right? That's where the role of simulation starts to come in. But for the simpler cases, the ones we'll talk about today, we can actually do it ourselves. A lot of pulse sequences are built something like this. We have, as we saw in the previous thing, some axis that describes what's happening to the gradients or what's happening to the RF pulses. And more often than not, I think it's fair to say, there's some kind of contrast module we manipulate the spin system in some way, and then we have some imaging module where we're sampling or getting a snapshot of the state of the magnetization at a particular time. And so there's lots of examples of these things, but for contrast modules, you've already seen inversion pulses. We won't get into the details today, but there are so-called T2 preparation pulses that emphasize T2 differences. There are pulses that will null fat, so we can get rid of fat in our images pretty well. There's other pulses called tagging pulses that are used for different applications. The idea is that there are combinations of RF pulses and gradients that we might use to manipulate the contrast, but manipulating the contrast is different from imaging, and that's what happens on the second part there. After we manipulate the contrast, it's really slow. Okay, let's take a 30-second time out here. Reboot one thing. Sorry, guys. I got a Faraday cage around my router. Almost back in business. Hopefully. Okay, so sorry about that. We were talking about contrast modules, and then the question is, or the subsequent thing that can happen is the so-called imaging modules. And we'll learn about both the contrast modules and the imaging modules as the course develops. If you've heard, learned, know something about MR already, there's lots of ways that we can do the imaging part of the experiment, right? So-called gradient echoes or spoiled gradient echoes, so-called spin echoes. Those are sort of the next two lectures. And one of the unfortunate things about MR is there's not really a completely agreed upon nomenclature. And so the same thing typically goes by at least 3 or even 4 different names. There's the inventor called it something and wrote a paper about it, and then the 3 major manufacturers bought it and put a trade name or a marketing name on it. So the same thing has 4 names, and it's I don't know, I think it's a terrible thing. So what's underneath here is just these other names that are referred to or related to the sort of major categories of pulse sequences. If you go down this avenue of getting into MR research, there are good sort of lookup tables for who calls what, so you can keep it all straight. So the question and the thing that we'll be working on today is how do we keep track of the magnetization's history, right? We have some building blocks, we have some tools, but I want to show you a procedure whereby we can actually do this. And to do that, we gotta get on the same page about our nomenclature. So we're gonna do this a bunch in the next few lectures, so it's a good thing to get the handle of. The top 2 things are just nomenclature we use to describe what's happening to the MZ, or the longitudinal magnetization. So the top one is the MZ magnetization immediately before, so at time 0 minus, for the nth event. You're going to see a series of events, the first, second, third, fourth event. So this is what's happening immediately before, or the state of the MZ magnetization immediately before some event. Think of it as an RF pulse, for example. What follows is almost the same thing, right? It's the MZ magnetization immediately after the nth event. So we usually have a state of the magnetization right before an RF pulse, and it got to that state because of things like relaxation, and then the RF pulse acts on it and does something, and that produces a new state of the magnetization. So this is the state of the magnetization after the nth event. And we borrow that same nomenclature for keeping track of what happens to the transverse magnetization. We can talk about the transverse magnetization immediately before the nth event, and the transverse magnetization immediately after the nth event. We'll, for the most part, stick with this nomenclature, and you'll get the hang of it as I work through a couple of examples. We talked about this briefly before, but I'll just remind you again. We've thought about free precession, forced precession, the laboratory frame, and the rotating frame, and relaxation, and all these things. It's good to work through those different examples and understand sort of the mathematics of those things. As it pertains to the rest of the class, we really only care about two particular cases. One is we're going to work just in the rotating frame. So probably starting today, I'm a little less careful about my primes, just because it's a little bit easier to work that way. And so the first thing we care about is free precession with relaxation. We definitely care about relaxation when the spin system is just free to precess. We're not acting on it with B1 pulses. When doing so, we have two expressions. You're going to end up memorizing these because we're going to use them so much. The first is just what happens to the MZ magnetization as a function of time. That's got two components, right? First component's the decay of some initial condition, whatever it is. The initial state of the magnetization is unstable and it tends towards equilibrium, which is what the second term represents. The second term tells you MZ is going to get towards equilibrium if you wait long enough. The other thing that we care about with regards to free precession and relaxation in the rotating frame is what happens to the transverse magnetization. And this is a little bit simpler, right? Because as soon as you generate transverse magnetization, it just wants to decay. And it decays according to however much you generated on the transverse plane, the so-called initial condition, and then it decays as a function of time, or whatever that tissue's T2 is. And so we're going to use these expressions every time we enter into a period of free precession. And periods of free precession are basically the times in between RF pulses. So mostly what we're going to do today is just have a series of RF pulses. And so if the RF pulse has already acted on the system, then we're just trying to keep track of the magnetization as it freely precesses but relaxes. Okay? The other thing that we care about is forced precession, but we saw it last time. Forced precession, we don't typically keep track of the relaxation term. Do you remember why? Yeah, exactly. So the events of forced precession are very short time events, milliseconds, right? RF pulses are short. And during those intervals, we don't typically care about relaxation. Is that an absolute truth? No. It really depends on the details of what your experiment is all about. But it's a broad assumption that we'll use for this class. And so this looks a little clunky. You've seen it a couple times. You've worked with it some. And it just tells us this is the RF pulse operator, right? The hard pulse operator. If we have a flip angle, we have a phase, we can create this operator, we can fill it in, and it will tell us how to rotate our magnetization immediately before the event, right? And it will produce a new state of the magnetization on the left-hand side. This is what's happening to the whole magnetization vector, right? Now, we're going to shorthand a bunch of this because for today, we're only going to care about 90-degree pulses, and we're only going to care about inversion pulses. And so we actually won't go through the sort of matrix formulation. You probably should or could just as an exercise, but we know pretty quickly what happens to the magnetization if it's an inversion pulse. And we know pretty quickly what happens if it's a saturation pulse. And we're not going to keep track of the phase today either. So this is kind of the most formal way that we can deal with it, but we'll worry to put in the phases and flip angles that we're using today. This will just be a matrix of zeros, ones, and minus ones. So here's what I'll call a typical pulse sequence. And it just is represented by an RF pulse, some intervening time, and then a second RF pulse. Usually the time between RF pulses we refer to it as the TR, the repetition time. And most pulse sequences, we're going to have to play hundreds or thousands of RF pulses, each separated by a constant time TR. So remember that TR in general is the separation between the first pulse and sometimes some other action in between, but then the second pulse. So that's the pulse separation time. And so we can start off with a simple initial condition, and we'll almost always start with this condition, right? We have the bulk magnetization immediately before the first event. And I'll label the events event 1, event 2, right? So the bulk magnetization immediately before the first event is just our M0 vector. It's just our equilibrium vector. And we'll always specify that as the 0, 0 M0 vector. That's the resting state of the magnetization if we haven't done anything yet. Cool? Okay. So then what happens is this is the state of the magnetization, right? That magnetization immediately before the RF pulse is acted upon by an RF pulse. Here we're representing the RF pulse as the operator. The RF pulse is that matrix. That matrix acts on a vector and produces a new vector, right? And so this expression here, this is the bulk magnetization immediately after event 1. Makes sense? Matrix operation is a little weird, right? Because the pulse sequence is going along from left to right, and the matrix operators are going right to left, so you have to keep track of things. But the point is we can keep taking the state of the magnetization, act on it by the right equations, whether it's forced precession or free precession, and it'll tell us the new state of the magnetization. And if we carry on with this, for example, we can talk about what's the state of the magnetization immediately before time point 2. Okay, so the state of the magnetization immediately before time point 2. We've acted on it by some RF pulse, and now it's just freely processing, right? That means it's just relaxing. And so now we can use here, I've shorthanded it as with the relaxation operator. Right? The relaxation operator depends on T1, T2, and how much time has elapsed. This is just, I'm just trying to give you the structural workflow for what we're going to do more for a specific example in just a second. And so this takes the state of the magnetization, right, immediately after the first RF pulse. So that's the magnetization right here. And it says, okay, I have to act on it with relaxation, and that will give me a new state of the magnetization. In this case, all the way down to immediately before the second event. So then the last thing here would be we have another RF pulse, right? That RF pulse is going to act on the magnetization immediately before the RF pulse. It's the state of the magnetization immediately before the RF pulse. That was the magnetization that we just figured out, right? It's some magnetization that was relaxing. That gives us a new state of the magnetization, and now we're going to act on it with an RF pulse. And so that's going to produce for us the state of the magnetization immediately after the second event. Conceptually, does that make sense? You have to keep taking the magnetization and act on it with the next thing, whether it's forced precession or free precession with relaxation. And then that keeps telling us what happens to the magnetization. But, you know, this is a very general framework. We'll look at a specific example in just a second. So the first example that we're going to work on is just saturation recovery, where we go through that process that I just described, where the RF pulses are just 90s. Right? We're going to play 90 pulse, spins are going to relax. Play another 90 pulse, spins are going to relax. And we'll look at sort of how that bears out mathematically. We talked about this already, at least the TR part, right? TR is just the repetition time. Usually it's the duration of what I'll call the basic pulse sequence repeating block. Pulse sequences are very redundant, right? We have to do the same thing hundreds or thousands of times. Why? Every time we are playing the events that accord with the TR, we're usually generating a single echo. And you don't know this quite yet from this class at least, but an echo fills a line of K-space, which is in some sense one piece of information that we need for building an image. We need hundreds of echoes to build images. In general, we're going to get at least one echo per TR. We'll see some fast imaging techniques later where we can get multiple echoes per TR. But for now, just think of doing some excitation, manipulating the spin system, and somehow generating a signal that we can record. The time at which you end up being able to record that signal is called the echo time. I don't think it's going to come up in today's lecture, but it's a good thing to be ready for. And so that's basically the time from excitation, so the beginning of that sequence, to the time of the maximum signal that you can generate, which we refer to as an echo. And that's the time that data is recorded. Data is recorded at the time of the echo time, and that helps us form the image. You won't see the TE come in quite yet. It perhaps stand to reason, but the TE will always be shorter than the TR. You'll see that sort of as things develop. And so this is the example I want to more specifically work on with you guys. And so it's simple. It's the saturation recovery pulse sequence. We have a forced precession event here with an RF pulse. The RF pulse is, we're not actually going to worry about the phase today. It doesn't always matter. We'll keep the phase the same, I guess, and we'll think of it as 0 if you want. And the amplitude is, or the flip angle is going to be 90 degrees. So we're going to play a 90-degree pulse. We have a time TR during which the spin system can relax. That's MZ can recover, and MXY will decay. And then we're going to play another RF pulse. The perhaps interesting thing is that the TR is usually a lot shorter than the T1s, sometimes even shorter than the T2s. And that means that you won't have complete magnetization recovery within a TR, right? How many TRs do you, or how many T1s do you need for complete recovery, roughly? Yeah, 3 to 5. 3 is on the low end, right? I forget exactly what it is, 87%. But by the time you get to 5 time constants, you're at 99, and then you've almost fully recovered at that point. So anyway, so the example that we're going to work through is the one that's here on the board. You'll have it in your notes. I'll flip over to my whiteboard thing in just a second. And we're going to talk about the basic pulse sequence is a 90-degree pulse, followed by just a period of time called TR, and then we could repeat that n times. We could do it 10 times if we wanted to, and it'll get a little boring if we go that far, but I'll show you how to generalize these in just a second. Questions about sort of where we're headed with this?
Could you explain how many T, what is that? How many T?
Yeah, so let's see if I go, just do it on, let's see if I do it. And so all I was suggesting or indicating is if we think about what happens to our MZ magnetization, where does it start? Let's say this is MZ, and this is time. If I play a saturation pulse, how much MZ magnetization do I have? 0. And so I'm going to be starting from this point here, right? And then the highest I can get with my magnetization is up to M9, right? But it's an exponential recovery process. And so if this is the maximum level that I can get to, we know that the equations for relaxation tell us that the MZ magnetization will eventually get up there, but it takes a while. And this time here is maybe 1 T1, and this time here is maybe 2 T1s, and then we get out to 3 T1s, until finally when you get out to, say, 4, 5 T1s, then you have something like 99% recovery. You've gotten almost all the way up. But you have to wait literally forever to get 100% signal recovery.
What's the pneumatic volume?
So T1 is tissue dependent, right? So it depends on if we're talking about white matter or gray matter. But in general, T1 is on the order of like 1,000 milliseconds. So once you've perturbed the magnetization, if it has a T1 that's 1,000 milliseconds, it actually takes several seconds to get back to sort of pure equilibrium state again. And we're all impatient, so we don't really want to wait that long, right? We want to do our imaging much more quickly than that. So then there's all kinds of ways to sort of manipulate the magnetization so we can scan it acceptably fast without waiting for fluid. I won't go through it maybe all the way, but the other consideration, of course, is what's happening to the MXY magnetization, right? And the MXY magnetization decays, right? Something like this. And again, it's going to decay more quickly, and so this is maybe, after 5 time constants, it's almost completely decayed. Yeah? So this last. So this is the setup. I cheated and I sat down and did some of this already. In fact, I think I gotta do it this way if you guys are gonna be able to keep up with what I have in mind here. Okay, so this is the setup for the problem that I was just describing. We have two RF pulses, and we could carry it past the first and second event if we wanted to. And then in the second chart underneath it, I'm going to keep track of what's actually happening to the state of the magnetization as we proceed. And then we're going to build up sort of, you'll see mathematically, we're going to build up two columns of what's happening to the magnetization. And so the first thing that we want to do is say, well, what's happening to our MZ magnetization immediately before, so 0 minus, our first event. That's our most initial condition. So what is MZ at time 0 minus? It's just equilibrium, right? We haven't done anything to our system, so it's just that amount, right? So always good to start with beginning, right? And so then we also have our MXY component. This is for the first event, immediately before we actually do anything with magnetization. So how much transverse magnetization do we have to begin with? Okay, so things get a little bit more interesting because now what we're going to do is we're going to play the RF pulse. And so the RF pulse is going to change the state of our magnetization, right? And we said it was an RF pulse, maybe it's 0 phase with a 90 degree flip angle, 90 degree being the most important part. And so now we can talk about what is MZ for the first event immediately after, times 0 plus. And what's MZ after a saturation pulse? Right up front, this is 0, right? And then similarly, we can say, well, what happens to MXY? This is again for the first event, but immediately after that first event. And how much MXY do I have now? None. And so we can see, sort of with RF pulses, we can trade the magnetization back and forth, right? We can trade the MZ to the transverse plane, and in fact, we can tip up the transverse plane to the longitudinal axis if we want to. We'll see that as a trick that we can do a little bit later. And so at this point, you have it in your notes, but you have to recall the equations of relaxation, right? And so we know that mz as a function of time is going to depend on mz0, whatever the initial state of the magnetization is, but that's unstable, so it decays away as a function of t1. And then we have our recovery term as well, which is m naught times 1 minus e minus 2t. So that's one expression for relaxation. And the second expression we have for relaxation is what happens to mxy as a function of time. And that just is mxy0, our initial condition, which is going to decay away as a function of t. So those are just the general expressions for what should happen to our magnetization. And so what we want to do is use those equations of relaxation to tell us where does the magnetization end as we get to time point 2. Let's do one thing here. So I'll keep track of my MZ magnetization in red. I'll keep track of my MXY magnetization in blue. And so we said it just from the expressions a second ago. Before the first RF pulse, we have no transverse magnetization, so the magnetization is just down here someplace. And then before the RF pulse, our MZ magnetization is all the way up here someplace. And this would be our M0 magnetization. The first event has now transpired, and so we know that our MZ magnetization is going to drop down to 0, drawing it a little bit of an angle. Don't worry about that too much. And then our transverse magnetization is actually going to tip all the way up. So that's just drawing out what these equations or expressions have told us so far. Yeah? So the next thing is, okay, we have to take our magnetization. We know what the state of the magnetization is immediately after the RF pulse, the first event, and what's the state of the transverse magnetization immediately after the first event. And now we have to use the equations to show what happens to the magnetization as the TR elapses, as time TR elapses. And so then what we're interested in then defining is the MZ magnetization immediately before event 2. And so we have two terms that we have to consider, right? We have this initial term and the second term, which is the return to equilibrium term. What's our MZ naught at this point in time? How much MZ do we have? 0, right? So this just looks like 0 times e to the minus t over t1. It's trivial, mathematically. And then we have the second term, which is the return to equilibrium term, and that's an m naught times 1 minus e to the what? We're trying to figure out what happens immediately before the second event. Yep, minus tr over t1. Obviously, this first term is sort of just a trivial term. The other thing we want to do is then keep track of what happens to our m, x, y, same time point, so it's immediately before event 2. And what's our initial condition for our magnetization? We're looking at this relaxation expression here, right? So what's the initial condition for our transverse magnetization at this point in time? Just M naught, right? So that's just coming down from here. And then it's going to decay, because that's what the expression for relaxation, the equations for relaxation tell us. And so it's M naught times e to the what? Minus tr. So that's pretty good. So we can go back and just plot out what's happening then. Let's do it with our Z magnetization first. Remember that the most magnetization we can have is going to be up here at M naught. So I'm exponentially approximating, getting closer to that state of magnetization. And I have some other event, this 90-degree pulse at the end there. So I'm going to show that my MZ magnetization recovers. But let's say it doesn't get all the way to M naught, right? My TR is a lot shorter than 5 T1s, so I'm only going to have partial recovery, right? So that's the history of how the MZ magnetization will change as a function of time. And now we got to keep track of what happens to our NXY magnetization. Is T2 longer or shorter than T1? Shorter, right? So is it going to get a lot closer to 0 or just barely get down to 0? A lot closer, right? So it's going to come crashing down. I'm not great at drawing exponentials, but maybe something like this. Right? And so this is a function of T2, obviously. And this here is a function of T2. So this is what I mean by sort of, we always have this new initial condition, right? It maybe doesn't feel exactly like an initial condition because maybe you're inclined to think, well, the initial condition is just like the very first thing that you start with. But we always have a new state of the magnetization, and that new state of the magnetization is one of two things is basically going to happen to it. It's going to be acted on by an RF pulse and give you a new state, or it's going to go through a period of relaxation and give you a new state. And so we didn't get to the, we didn't get all the way through this yet because there's a condition that I want to talk about that's called the saturation condition. And the interesting thing to sort of notice here is with this particular sequence of RF pulses, 90-degree pulses that are separated in time, you'll very quickly end up in what we call steady state condition. Because when I take this amount of magnetization and tip it down, I'm going to recover again. I'm going to recover back to the same level of magnetization. You quickly enter into this steady state where you pushed it down and it recovers as much as it can. You push it down and it recovers as much as it can. And it's doing the same thing whether you have 2 RF pulses or 150 RF pulses. I'll show that to you mathematically. But to do that, we have to talk about what's called the saturation condition. So questions on how we sort of went through the mathematics here? I don't know if I'm going too fast or I'm going too slow. We can pick it up if we need to, but I think we'll stick with it for now and then we'll develop this a little bit more just a second. Yeah? Okay. So then we come back to slides. And we talk about what's called the saturation condition. The saturation condition is a little bit confusing. Mathematically what it means is that the MZ magnetization immediately after some event, right? So those events are typically RF pulses. That's what we care about. If you have saturated the MZ magnetization, then immediately after an RF pulse, the MZ is 0. That is the so-called saturation condition. And it's a useful thing. So MZ is 0 after the event, after the RF pulse. And you'll see that this is true when you have a multi-RF pulse event, if you have several RF pulses. What's the condition that ensures that that's actually the case? So this is going to be true, that this condition will be met in a sequence of RF pulses. It's going to be true if the transverse magnetization is gone before the next 90-degree RF pulse is applied. Okay? That means there's no MX to convert to MZ. So think about that process of relaxation. We were just talking about what's happening to the MXY magnetization, right? MXY magnetization is going down, 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 down. But it hasn't maybe gotten all the way to 0. If it doesn't get all the way to 0 and I play a 90-degree pulse, my transverse magnetization will become Z magnetization, right? 2 90s make a 180. So there's a period of transverse magnetization decay. If I play a 90-degree pulse while I still have substantial transverse magnetization, I will generate MZ magnetization. And the saturation condition was stating that I would have no longitudinal magnetization immediately after that event. If I'm going to have no longitudinal magnetization immediately after an RF pulse, it means my transverse magnetization has to be 0, so I don't inadvertently tip it onto the Z-axis. Does that make sense? It's not an entirely obvious concept, but the state of the magnetization, we can tip it into the transverse plane. I can play a minus 90, which is just a 90 with 180 degrees of phase, and I can tip the magnetization back up. So if my transverse magnetization is anything non-zero, the RF pulse will generate Z magnetization. And that's, in principle, it's a bad thing, because you'll be mixing magnetization between the transverse and longitudinal planes. So how do we get that to happen? Well, one way you can ensure you have met the saturation condition is by making sure that your TR is a lot longer than your T2. Right? So your T2 is 50 milliseconds. If we go back to this plot here, if our T2 is 50 milliseconds and we wait 500 milliseconds or 5 seconds, then our transverse magnetization will completely decay. And when I play an RF pulse, there's no risk of me generating some longitudinal magnetization. There's actually a couple ways that we can do that. If you don't have your TR such that it's a lot longer than your T2, so maybe your TR is only kind of 3 T2s or something like that, and that's the state I was talking about. You'll have some residual transverse magnetization. The residual transverse magnetization can be converted back to MZ magnetization. You're effectively tipping it all the way, you're tipping it down again. It'll give you an MZ component, and that's going to corrupt or complicate your image contrast and lead to artifacts and things like that. We really like controlling the magnetization. There is actually a solution to this, that is to say if your TR is a lot shorter than, call it 3 T2s, and we can use what we call spoiler gradients. You'll remember when we were talking about gradients, we were saying that we could have a system of spins, and the gradients would cause spins to accumulate different amounts of phase. And if within a pixel you have your spins accumulate enough phase that they're pointing in all directions, then they can't generate a signal. There's no induction to be made in the nearby coil. So spoiler gradients are a way of dispersing the transverse magnetization and accelerating the apparent decay of the signal. So it's a combination of that dephasing plus T2 decay. So there are all these tricks in MR to get around these problems. But again, we would like to meet the so-called saturation condition. And we'll see what that does. In part, what it does is it allows for a steady state solution to arise if that saturation condition is either met, and it's met if your TR is a lot longer than your T2, or it's enforced, if you will, if you use so-called spoiler gradients to accelerate that transverse dephasing. Okay, so I'm going to go back into my problem. We're going to carry through again because we didn't get all the way there, right? We just got, I think, right before event 2. And I want to show you that this actually you can get into a steady state condition That's a useful thing. Yeah. So let's go to. Is that okay? And so those, what's there now is the state of the magnetization immediately before the second RF pulse. And we're just going to show what happens if we carry on past the action of that second RF pulse. So we want to talk about our MZ magnetization immediately after the second event. And if the saturation condition is met, how much MZ magnetization do we have after the second RF pulse? 0. Right? And so this was if the saturation condition. And so then the other thing to keep track of course, is what happens to our MXY magnetization, and that's immediately after that second RF event. And in that case, okay, so now I want to say what happens to the state of my transverse magnetization immediately after my the second RF pulse. Right. So this magnetization here, right? If the TR is sufficiently long, or the T2 is sufficiently short, or you play a dephasing gradient, then this transverse magnetization here is going to go to 0. And the amount of transverse magnetization I can get from that second RF pulse depends on how much magnetization I had on MZ, right? And so this MZ magnetization at the end of my RF pulse comes into this condition here. And so I can tip down onto the transverse plane as much magnetization as has relaxed along MZ. And so I have M naught times 1 minus E to the minus TR. And again, that's another example of sort of seeing how we can trade the magnitude of the magnetization back and forth between the longitudinal and the transverse plane. So this was the action going in this direction here was another 90-degree pulse. If we go back up to our diagram that we had, we're keeping track of our magnetization, we're doing our best. And that means, let's start with the Z magnetization. That means our Z magnetization, right after our pulse, comes crashing down because we played a saturation pulse, and we have no residual transverse magnetization because the saturation condition is met. And our MXY magnetization comes tipping up, but it doesn't. We don't have the full M naught magnetization available, right? We only have as much magnetization as there was time to recover, and that accords with the time TR. So the next thing, and we'll develop this in just a second, will be our transverse magnetization can only do one thing. And so our transverse magnetization here will just be decaying as a function of time. Can't show it all the way across, obviously. And our MZ magnetization will again begin to regrow back towards that equilibrium state. Mathematically, what does that end up looking like? Mathematically, we can think about what happens to the magnetization if we wait another interval TR. So, say we wait another amount of time TR. And so we could consider what is our MXY if we got all the way out, but just before the third RF pulse. We didn't play the third RF pulse. We have a state of MZ magnetization, right? We have this M naught term. That's on the transverse plane, but it's going to decay, right? And so after a time tr, we still have, that is our initial condition, m naught times 1 minus e to the minus tr over t1. But we've decayed that transverse signal, right? And so we have to multiply using the equations of free precession with relaxation, and we have an e to the minus what? How much does the transverse, in what way does the transverse magnetization decay? According to, yeah, e to the minus tr over t2. We can similarly keep track of what's happening to our MZ magnetization, right? So on the left-hand side here, I can say my MZ magnetization all the way out at time point 3, but just before I play the RF pulse, right? What was the initial state of my magnetization? What's my initial condition for MZ at this point? It's just what's coming in from above, right? So I just have 0 times e to the minus tr over t1. So that's the trivial term, if you will. And then you got a little crowded, so I'll write it underneath here. Plus this return to equilibrium term, right? It's always the same return to equilibrium term. You just have to figure out how much time. And so we still have an m naught times 1 minus e to the minus what? We're going from, I didn't show you the diagram, but from event 2 out to event 3. Right? Yeah. Yep. E to the minus tr over t1. And so this is this process of keeping track of how the magnetization moves around, how we trade MZ magnetization to the transverse plane. Once we've done that, it's subject to T2 decay. We might have another RF pulse come along and we can tip the magnetization back up, or the transverse magnetization decays. We just kind of go back and forth keeping track of it. If that saturation condition is met, right, and that was really this right here, the highlight on the right, that's saying that your transverse magnetization is totally gone at the end of the TR, then you do end up with this, this sort of general solution that comes out of it. So I'll move up a little bit. And what you can work out is that the MZ magnetization for any event n immediately before the RF pulse is just m naught times 1 minus e to the minus tr over t1 plus the amount of magnetization you had from the previous event. So we write that as n minus 1 times e to the minus tr over t. Now, if the saturation condition is met, then this term here just goes to 0. You can't generate that component. And so you could more generally say that it's just m naught times 1 minus e to the minus tr over t1 for specifically n greater than or equal to 2. So during that first RF event is unique in this case, right? You start off with full m naught, you tip it down, and it recovers as much as it can, but it only can recover for interval tr. With the saturation sequence, you're always going to get back the same amount of magnetization after that, because you're always just waiting the same interval tr. And so you end up with this sort of steady state solution. As long as you're talking about, as long as it's for the second or greater RF pulse. You could carry this through if you want to. You could work it through RF pulse 3, 4, 5, 6, 7, 8, 9, 10. You'll always get to the same state of magnetization for immediately before the RF event. We could also write down what happens to the transverse plane, right? And so for the transverse magnetization, which is, we can generalize it. So this is transverse magnetization immediately before the end RF event. And that's going to depend on the state of the transverse magnetization for the n-1 event at time 0 plus. So immediately the event before, but right after the RF pulse. And that's going to just decay as e to the minus t over tr. And so we'll go through this, and we'll go through another problem actually in a little bit, but this helps sort of outline that procedure I was talking about before. You have an initial condition, transverse magnetization, longitudinal magnetization changes because you have a new state of the magnetization, and you can keep working through periods of free precession or forced precession. Questions about how I work through that problem? So let's think about some other possibilities then. So the expression that we just worked out was this expression here, right? So you had some, I think I had an M naught in there. That's, you could write this as an M naught, 1 minus e to the minus TR over T1. That's the state of the magnetization, the MZ magnetization at least, at the end of that TR, once you're into the second, third, or fourth TR. How much magnetization you actually have available to you is actually dependent on the proton density, right? So we can have a lot of magnetization if you have proton-rich environments. Other tissues have lower proton densities, and so the actual amount of bulk magnetization available to you is a proxy for the proton density. And so this expression here, if you were to try to record the signal at the end of the TR, right, so the amount of time that's elapsed here is the TR, if you try to record that signal, we can get an amplitude of what we call the FID. We'll talk more about what's called the free induction decay signal a little bit later. But this tells you about the amplitude of the available signal for you for this saturation sequence. So what's interesting about this? Well, this is the amplitude of the signal immediately after that, say, second RF pulse, right? Second or third or fourth. This is how much magnetization you could possibly have, or how much signal you could possibly have. Takes into account the proton density, and here we're assuming that the process of imaging itself isn't going to mess with the state of the magnetization. We'll see in just a second, actually, I'll show you an example that the RF pulses we need for imaging actually perturb the magnetization. So even though we can have these so-called contrast modules to get the magnetization to do something, the imaging itself will perturb the magnetization as well. Okay, so the final equation that we can make of this is what's on the bottom here, which just, we don't know how to do the imaging experiment yet, right? But we know that things like proton density can be functions of space. The proton density is not the same at every pixel location, right? And we don't expect the T1 to be a constant either, right? T1 can be a function of space as well. We don't know how to do the mapping experiment, the actual imaging experiment yet. But because from this expression we can recognize that the amplitude of the signal we can record depends on, say, proton density in T1, then we can expect that the image that we could generate would depend on proton density, and would depend on T1. Now, with the saturation recovery sequence, there's only one thing that we can control, right? What is it that we actually control if this is our experiment? The TR, right? And so what amplitude or how signal rich this experiment will be will depend on how well you choose your TR relative to your T1. And you saw a little bit of that in your homework assignment where we talked about contrast, right? It depends what your target is. Is your target getting maximum amplitudes, or is your target getting contrast between two tissues? If you chose a really, really short TR, what would this expression reduce to? What if the TR is almost 0? What happens to this exponential term if the TR is almost 0? This goes to 0, right? And so what you're left with is just this proton density term. And so if you want to, with the saturation recovery pulse sequence, you would play a saturation pulse and try to do your imaging right away. And if you did so, you'd end up with a very proton density weighted image. If you chose your TR to be kind of on the order of your T1, which means that this component here is significantly non-zero, and you start adding so-called T1 weighting. The proton density term is always in front. We can't, it turns out in all of our images are sort of colored by proton density. Fortunately, proton density is relatively neutral across tissue types, or most soft tissues at least. And so the point is, you could get a proton density weighted image using this sequence. You could get a T1 weighted image from this sequence. And the only thing that you can control to go between those two states, if you will, is the repetition time, the time between the RF pulses. How much recovery do you allow for? Okay, so that was the expression on the top there is just the same. And I guess I sort of worked through this example already. If your TR, I guess I said it all wrong, right? If your TR goes out to infinity, then this term is going to 0, right? If your TR is 0, then this term is actually really close to 1. And so if what you want is a proton density weighted image, then you choose these long TRs. And that should make sense, right? You're taking your magnetization, you're tipping it all down to the transverse plane. And if you image that magnetization, almost all tissues will give you the same amount of bulk magnetization in the transverse plane because the proton densities are so big. And then you wait long enough for any tissue, regardless of its T1 to recover, then the signal intensities will really just reflect and depend on the proton density. So again, the only thing you really control is the TR. We can actually work through optimizing contrast for a sequence like this. I won't go through the mathematics of what this actually looks like, but it's similar to what you saw in your homework assignment, which is to say if you want the maximum contrast between tissue T1, tissue A, that is T1A, and tissue B with T1B, then we can figure out the optimum TR and get it to maximize the contrast between these two things by taking the difference of the signals and differentiating the signals. I like thinking about applications, so that's the mathematics of how that saturation recovery sequence works. Let's think a little bit about why or how we might actually use this. There's a big movement, certainly in cardiac imaging, but in other areas as well, to actually do quantitative mapping. How can we measure things? How can we measure the T1 of a particular tissue? How can we measure the T2 of a particular tissue? We call these mapping sequences. And so in this particular example, this is a sequence that's called Sasha. Sasha is related to using a series of saturation pulses. And the images that you'll see across the top are different heart images. And what's shown is an image or a snapshot of the magnetization if you've waited various amounts of time. And so the first one here is the so-called non-saturated condition. So this is similar to playing a saturation pulse and then waiting forever. Right? If you wait a very, very, very long time, everything's recovered, and you get basically a proton density weighted image. And so this is very close to a proton density weighted image. The other possibility is that you play a saturation pulse and you wait a couple hundred milliseconds and form an image. And if you form images at different points in time, different durations after that saturation pulse, you'll be capturing the recovery of different tissues at sort of different points in their recovery curves. And so all that's shown here on the bottom is the recovery curves, in this case for the heart or the myocardium and the blood signal, if you get a series of images at different saturation recovery times. So you saturate and then you allow the magnetization to recover for 600 milliseconds or 120 milliseconds. And then we know what the equations of relaxation look like, and so we can just fit exponentials to these functions, and then in this case create maps of the T1 value. So if you can get these snapshots at different points in time in the recovery process, you can get a T1 map. And all they're showing here is that for the heart here shown in this circle is mostly yellow, and that means that the T1 value in the heart is about 1,000 milliseconds, and this is just the sector plot of the same, and they're comparing that here to blood. And so you can see that the T1 of blood is much longer, and they can measure the T1 of blood, they can measure the T1 of the heart.
What is the TS?
It's the saturation time. So you play the saturation pulse, and then you wait 600 milliseconds or 120 milliseconds, and then read out. Yeah. So in the normal case, that's maybe not especially interesting. The second example here is what happens in the case of a patient that has an infarct. And so as a matter of the physiology, if you will, if someone has a scar, they have a heart attack, and they develop scar in their heart, that scar has very different tissue properties. And in fact, after the administration of a contrast agent, the contrast agents tend to absorb into areas of scar. Contrast agents are T1 shortening agents in general. So it makes the scar appear really bright, or as if it has a short T1. And So this is that same mapping experiment. I'll show you a little bit more detail about how they do the actual experiment in just a second. But the point is that on the mapping image, you no longer see this perfectly homogeneous sort of myocardium. You see myocardium that's it's a little ragged, if you will, but in the area of the infarct, it's markedly different, and the T1 value is maybe 200 milliseconds. The other thing that's really different here, of course, is that they gave a contrast agent that's in the blood, and so now the blood has a really short T1. So in the previous slide, the blood T1 was like 1600 milliseconds, but when you add the contrast agent, the blood T1 goes down quite a bit to, say 300 milliseconds or something, 306 milliseconds. So this is just, one possible way of using saturation pulses to, in this case, measure the T1 of tissues. You sample the magnetization at multiple time points, fit an exponential, and you can do so-called mapping. And this is, at least right now, there's a lot of investigation as to how diagnostically useful this is, how quantitative it is, how much it tells us about, say, the severity of disease, for example. So a little bit more detail about how they actually go about doing this. This is interesting. It's pretty clever, actually. So across the top is the ECG pulse, right? So they're measuring someone's heart rate, so they can synchronize the imaging to that individual's heart rate. And the very first image they acquire is the no saturation sequence, right? They're going to wait for the heartbeat, and then they're going to do some imaging. One thing you should notice is the imaging always happens at the same part of the cardiac cycle, right? That means that the shape of the heart is going to be identical because it's the same amount of time after the beginning of the cardiac cycle. And so they're just moving around the saturation pulse relative to when they do the imaging. So the very first one, they actually don't do any image, but they don't do any saturation pulse. We'll talk about that in just a second. Second heartbeat, they play a saturation pulse, they wait a long time, and then they get the images. So you saturate it, and then you wait for recovery, you take your image. And they're just advancing the saturation pulse relative to the imaging pulse until at the very end, they're saturating imaging, right? Saturate and right away get an image. So the TS in that previous slide is going to be really short here. There's not very much time for recovery at that point. Now, what's interesting is maybe this first one here, the no saturation case, right? This is actually the same as playing a saturation pulse, but waiting a very, 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 very long time. And so they basically, rather than doing that, they just don't play the saturation pulse and generate the image. And so that's I think a kind of a clever trick to getting around waiting forever, right? The magnetization before this has already waited forever. Maybe there was a saturation pulse played 3 years ago, right? So I think that's pretty clever. I won't drill into this too hard, but what's being shown here now is just what happens. This is simulation, so this is using the block equations, using the formalism that you guys are slowly putting together, and what it shows a couple of important things. It's keeping track of the MZ magnetization. It's keeping track of the transverse magnetization. And so what you can see, say in heartbeat 1 here, is that MZ magnetization played a saturation pulse, right? And the MZ magnetization is now recovering until it gets up to this point here. Now this business here where it dips down and you have this funny curve, that's the effect of imaging itself, right? So what they want to do is, what you would ideally like to do is perturb the magnetization, let it recover, and get a snapshot without actually somehow perturbing the magnetization. But imaging itself perturbs the magnetization. So if you're a good physicist, you just keep track of everything, and that's basically what these guys did. So they can keep track of the magnetization as it's recovering. They know what the imaging pulses will do to their magnetization. So they can interpret the actual signal that they measure in the context of all of the RF pulses that were played, the saturation pulses and the imaging pulses, which we haven't quite learned about yet. And then they're doing the same thing to keep track of the transverse magnetization. And the last thing they have to do is they just have to reorder that information according to when it actually accords with just the natural relaxation curves that we've been talking about so far. What do I mean? Well, that very first image that they acquire was the no saturation condition. The no saturation condition is how much magnetization you have if your TR is infinitely long. And so again, it's just a clever approach of mapping or measuring the T1 in tissues. The blue curve just tells you what is the actual fitted recovery to the data that they measure, and then the little red lines are saying, well, the magnetization itself is actually perturbed partly by the imaging process. So it's a lot more sort of detailed and the kinds of things we can keep track of on the board, right? We have to keep track of it by doing block equation simulations, but it does have the effect of allowing them to map things on T1, which is really interesting.
What's the flip angle from the readout?
Yeah, it's a great question. So you're asking about the readouts, and the readout is when they actually do the imaging part of the pulse sequence here. And I don't remember whether they're using what's called a balanced steady state free precession readout or a gradient echo readout. If I look at this, it looks like balanced steady state free precession, and so it's probably like 60 degrees or something like that. I'd have to go back and look at the paper to say for sure. Okay, so that's just one clever sort of option. Why don't we go ahead and take a quick break? I know I rolled past kind of the midway point. Why don't we take a quick break, and then we'll try to come back to inversion recovery. And I also want to get you back your homeworks all in the next 20, 25 minutes.
I think it's pretty predictable. It's just
Yeah, no, I stopped checking the French and let Luigi know. I asked him what time he thinks should be. Well, I think he'll be done at 6:30, 7, and then I think so. Sinjo is working on MRI, real-time guided stuff. So I think he's gonna come do that again tonight. With
Yeah. It looked pretty good. I mean, we got it for the first time.
we're not injecting yet.
Yeah. We talked about that. I think it's maybe an idea. It's in vivo.
Yeah, because of the kids. So I know the next set. So I mean, not the one in March, but it's the in-park model. Planning on like down the road a little bit.
Yeah.
That you should definitely do like employments for him, right?
Yeah.
So then we'll see it in we'll see it in park.
Yeah.
Next week.
Yeah.
So we do that. No, those are so nice with highlights. Especially in the back on
Oh, amazing.
Get the monkeys in. Well, you do all set by 9. Yeah. And it's another time.
All right, let's go ahead and peel through this. I think what I'll try to do is we'll work through one more example because I think it's really important to get through it. I won't get to just some of the slides at the very end which discuss various applications, similar to what we just talked about the Sasha sequence. I won't get a chance to talk about the other applications, and we'll figure out how to make up for that a little bit later. And so here you've seen this a couple times already. So the sequence that we're building up to is actually what we call the spin echo inversion recovery sequence. We're not going to see the spin echo components of it today. What we're going to do is just the next example, which is instead of a saturation pulse, it's the inversion pulse, and then what happens in the magnetization. It's a similar example, but there's a couple smaller details. This you've seen a couple times before, which is just telling us that as a consequence of playing an inversion pulse, if we time the imaging experiment, right, to be some time after that inversion pulse, we can get very different forms of image contrast, and that's a so-called strength of MRI. And of course, you can do this in any imaging plane as well. And so here, the pulse sequence that we're going to work through is a little bit different. We'll basically spend probably 15 minutes or so on the board, and then that'll wrap up the lecture. And it looks like as follows. We start with an RF pulse that's 180 degrees, so it's an inversion pulse. And we're not going to, again, worry about the phase. We'll just let the phase be 0 degrees for everything. And then there's some period of relaxation. That means we've inverted it, and the magnetization is recovering, right? It's going back towards equilibrium. But at that point in time, we play another RF pulse, a 90-degree pulse, and that's so we can generate some transverse magnetization. We have to generate some transverse magnetization if we're going to be able to form an image, right? We need some transverse magnetization because that's what's actually detectable. So we're going to play an inversion pulse, we're going to play a saturation pulse, and then we're going to wait some other period of time. And the two timing, well maybe three timing parameters here to keep track of is the inversion time, and the inversion time is how much time has elapsed since the inversion pulse. And then we have what we call a TD, or a delay time, which is the time between the 90 and the 180. And then the repeating element here is this 180, 90, all the way up to the next 180 pulse. And so the TI plus the TD is the TR. Right? So lots of timing parameters. But the repeating block is from event 1 to just before event 3. So that's a time TR. So that's the setup for the problem. I'm going to flip over to my sort of whiteboard, and we'll try to keep track of what happens to magnetization for this one. Yeah? I think I should be able to put this together already. So this is the setup that we're talking about, which is keeping track of. And it starts off very much like the previous one. So in the interest of time, we'll go a little bit quickly here. And so we want to know what's our MZ magnetization immediately before time point 1. And this is just our typical initial condition. What is it? How much do we have before we do anything? Set none, right? And then we also have to keep track of what happens to our MXY magnetization. So MXY immediately before 1. And how much do we have? 0. Right? So the slightly different thing that's happening now is we're playing a 180-degree pulse, right? And so our MZ magnetization immediately after the first event becomes what? How much MZ do we have? Yep, minus 1. Right? And also important is keeping track of MXY. So MXY immediately after that first RF pulse. How much MXY do we have after an inversion pulse? 0. I mean, that's the ideal state at least. So we can keep track of what happens to our MZ magnetization again. Before the RF pulse, we had none, right? And after the RF pulse, it comes down all the way to being inverted. And we can keep track of what happens to our transverse magnetization, and it started off 0 and just continued to be 0. So nothing too interesting is happening yet. Okay, so we have a state of our magnetization after our pulse. Now we have to allow for it to recover. And so our MZ magnetization, we're going up to event 2. So this is immediately before event 2. the amount of, what's our initial condition? We have to have a state of magnetization that's decaying that we bring in. Just minus M naught, right? This term just comes in here as the decaying term, e to the minus. The duration here is the Ti, TR. So that's the component of magnetization, the pool of magnetization that's just decaying. And then anytime we have a period of free precession with relaxation, and we're trying to get back to equilibrium, so we'll always tack on our M naught term. So it's M naught times 1 minus E. What's the period of relaxation? We're talking getting up to just before time point 2. It's just minus Ti. Yeah? So there's some M naught terms that... Sorry, yeah. So this, here I'll do this just, so this should be T1. Right? So that's what happens to our NZ magnetization. There's some M naught terms that we can combine there, right? And so I can tack that down. You saw this in your first homework assignment as well. So you have an M naught times 1 minus 2E with minus Ti. We need to keep track of what happens to our MXY magnetization. So we have our MXY magnetization. We're going up to event 2, so headed towards event 2, but immediately before it. How much transverse magnetization do I have? Still none, right? I didn't have any, and nothing just decayed, so to speak. So we can come back up and say, well, what's happening to our MZ magnetization, or MXY magnetization rather. MXY magnetization is just continuing up to time point 2. Our MZ magnetization does something a little bit more interesting, right? It's beginning to recover. I'm going to show it as recovering, say, all the way up to there. Depends what the T1 is as in terms of how far it will actually get, right? So now the next thing here is what happens with the RF pulse. Oops. I have to have the action of this RF pulse on my MZ magnetization. Let's scroll up just a little bit. So I have my MZ magnetization immediately after my second RF pulse. How much MZ do I have after a 90 pulse? None, right? And I have none because at least at this point I didn't have any transverse magnetization. Right? There's no transverse magnetization to tip onto my z-axis after that 90. On the other hand, my MXY magnetization gets a little bit more interesting, right? So I have my MXY magnetization immediately after time point 2. That's this 90-degree pulse, right? And so now I'll be taking the longitudinal magnetization that I had and projecting it onto the transverse plane. So I'm just inheriting this magnetization here. So I have an M naught times 1 minus 2E minus Ti over 2. And now I have another period of free precession, right? So let's scroll up a little bit here. And I want to say, okay, what happens to my MZ magnetization as I head towards time point 3? So my MZ magnetization all the way up to just before event 3. This is a period of relaxation, obviously, free precession. If I want to, I can write my MZ naught e to the minus, say, TD over T1. What was my MZ naught term, though? 0, right? So this term is 0. But I have to add back in my return to equilibrium term. It's always there. So I have a plus M naught times 1 minus E to the minus TD over T. Similarly, I want to keep track of what's happening to my transverse magnetization. I'll write it just underneath here. So I have my MXY magnetization. This is heading out towards event 3, but not quite getting to it, so at time 0 minus. And I have the state of transverse magnetization that I had before, but now it just further decays, right? And so I begin with my initial condition, which is m naught 1 minus 2 e to the minus t I over t 1. And that's just this term coming in. But now I have this period of time during which the state of my transverse magnetization can continue to decay, and that time, I'm getting a little cramped on space, but I have to multiply this term here by e to the minus, I could write it in different ways, but I'll write it as, say, t d over t 2. So we can come back up and think about what's actually happening to our magnetization again. If we look at the MZ magnetization, I played a 90-degree pulse, and so my MZ magnetization goes back down to 0. And now as I approach event 3, it's going to be recovering towards, but not getting all the way back to equilibrium. And I can keep track of what happens to my MXY magnetization as well. My MXY magnetization inherited, or we projected what was on Z onto the transverse plane. So my MX magnetization goes up, however much I had on Z. But that magnetization is not stable, right? The transverse magnetization decays. And so this magnetization will be decaying and probably get pretty close to 0 by the time we get to that third event. So just the reminder that we don't get quite back to the Okay, so our goal is to figure out all the way out at event 4, right? Event 4 was that second 90-degree pulse, and right now we're just before the second 180 pulse. So we got to say, what happens to our magnetization after we play another inversion pulse? So that's going to get us out to our MZ magnetization immediately after time point 3. And that's going to take whatever Z magnetization we have and invert it, right? And so the magnetization that we have is this term here coming in. And so we just end up with a minus M naught times 1 minus E to the minus T D over T. We just inverted however much we had on the Z-axis. What does the inversion pulse do to our transverse magnetization? Transverse magnetization. Nothing, right? And so we can write our MXY magnetization. This is immediately after the inversion pulse. But our transverse magnetization for a perfect inversion pulse is unaffected. And so this still just retains that same term. We just have M times 1 minus 2 e to the minus t by t1, which is decayed by e to the minus t d over t2. And that's kind of an interesting term now, right? Because it has the mixed effects of t1 and t2. We're teasing the magnetization, right? We're putting it along Z, we're putting it along transverse, we're putting it along Z, we're putting it along transverse. And as a consequence, you're incorporating both T1 and T2 relaxation into the available magnetization. So then the last thing that we'll do is carry on through to what happens just before we're at this point here where we're at time point just after time point 3, and I want to say, well, what's my magnetization sort of before and after time point 4? And so think about what happens to our MZ magnetization immediately before time point 4. And that's just a period of recovery. And so we have an initial state of our magnetization that's going to be, we'll have time to recover. So this is a minus m naught times 1 minus e to the minus t d by t. has an interval ti to continue recovering, or decaying rather. So it's an e to the minus ti by t1. That's the initial condition is decaying. The initial, whatever the state was, is an unstable state. And then there's still this return to equilibrium term. I'll go ahead and write it here, right after it. And that's again, it's just this m naught term times 1 minus e, depending on how much time has transpired. In this case, we have the time ti has transpired. So it's e to the minus ti by t1. Algebraically, perhaps no surprise, there's some terms to combine there. If we pull the m naught out in front, then you'll get an expression that looks like m naught times 1 minus 2e to the minus ti by t1 plus an e to the minus tr by t. Yeah, it's tr, sorry, I made a...
Should just be dd.
Is it? No, it's the E. It's the second E.
T plus TI.
I'm gonna apologize and let you guys sort out. I'm sure the last expression is right. I think I have a tr minus ti that I called a td. It might be right. The last expression is right. So let's see. And this here is a tr minus ti. So I think it was exact. So let's quickly examine what happens in the transverse magnetization for the same time point. So we have an mxy at time point for immediately before that last R pulse. And it's going to be the magnetization that we had before, but it can decay for even longer. And so it's m naught 1 minus 2e to the minus ti by t1. And then we can multiply by, in this case, e to the minus tr by t2. We were decaying just at time t2, and then the signal just continued to decay through the rest of the tr. And this component here, as I'll draw it in just a second, this is going to be, or at least we'll assume that it's approximately equal to 0, and that makes sense for, let's say, t2 being much less than t. Not always the case, but a reasonably good assumption most of the time. Let me see. Yeah, okay. So are we okay with how that played out? I think it's right. Yeah.
At time 3, the MF1 0 plus.
Yes.
Yeah. Should that the MF1 also free from 30 degree?
It's an interesting question. What we're not, yeah, so you're asking if this magnetization here, it just saw the 180 pulse, right? Should it also change sign, right? I think that's what you're asking. Should it be a negative? And the answer is no. And the reason is what we're not doing is keeping track of the phase. You'll see this come up in the spin echo lecture. So picture this. This is my MZ magnetization, and this is my transverse magnetization. What this captures, everything that we're capturing here is just the magnitude of the magnetization. Okay? So for time point 3, immediately after the inversion pulse, I have my fingers as the transverse magnetization, and I turn it over. Right? That's the inversion pulse. So you saw the MZ got inverted, and so the minus sign came in. But my transverse magnetization hasn't changed in magnitude. And this is only keeping track of magnitude. If you wanted to be careful, and we'll do this later actually, we'll keep track of the phase. Right? And then it'll really matter. right? Did you take your magnetization, which is, let's picture my transverse magnetization as just my thumb, and now if I invert it, of course it points in a different direction, right? But I could also invert it this way, and maybe it doesn't change direction, right? And so the phase of that 180 pulse will tell you different things about what happens to the transverse magnetization, but we haven't even taken that into account. So that gets us through sort of the derivation part that I wanted to get through, and I think I'll just try to show you one last thing. Oops. Just back to the slides really quickly. That same final expression will help you understand these expressions where we can talk about the amplitude of the signal. So we play that 90-degree pulse, and the amount of longitudinal magnetization that we have, the last thing we had on MZ, looked very similar to this term here. And so when we play that last 90 pulse and generate transverse magnetization, we can generate what we learn about. It's called the FID. It's a state of transverse magnetization that depends on the T1 of the tissue, depends on the TIs and the TRs that you choose in that pulse sequence, and it depends on the proton density of the pulse sequence, the proton density of the tissue as well. And so the final image ends up being this product of the proton density and this kind of funny function of the tissue T1. And there's different parameters we can adjust, right? We can adjust the TR, that's a chosen parameter. We can adjust the TI, that's a chosen parameter as well. And so those are the things that help you control the image contrast. I won't go through the rest of the slides, mostly because I feel bad because it's getting late. If I have to, I'll put some things online. Questions about sort of how we work through the states of the magnetization? We're going to do this a few more times for a bunch of different problems, and I can guarantee you I'll have a problem like it on the final.
Just,
To be fair.
just for like completeness, can we just finish going through the diagram?
Yeah, sorry, yeah, of course. And so I think what you're asking is at the top. I didn't go all the way through what happens. And so the transverse magnetization there is in blue. We play, at the very end there, we play an inversion pulse. The inversion pulse doesn't do anything to our transverse magnetization. And so our transverse magnetization just kind of continues to decay all the way up to time point 4. More interesting, of course, is what happens to MZ. Our MZ magnetization gets inverted, however much we have. But remember, this is again less than the sort of equilibrium possible magnetization. It's down pretty far. And then leading up to time point 4, again, it's going to recover, but it's only going to get sort of so far. And so that was the state of the magnetization at the end of the mathematics that we did. We could carry through to time point 4. I don't know why I didn't put it in my notes. But time point 4 then would have you taking that MZ magnetization and putting it back onto the transverse plane. So your MZ would go down and your MXY would come up. So that would be the available amount of transverse magnetization. And that's the state of the magnetization that's, because it's the transverse magnetization, it's available for detection. We can pick it up, measure it, and it would tell us something about the underlying tissue. Because it depends on the very last expression that we have, right? So I'll let you guys do it. But you should work out for yourself what is MC at time point 4 immediately after. And you should work out MXY time point 4 immediately after. And that'll tie right back into the slides.